Hey, Vsauce, Sam here. This is a parody of a scene in Interstellar where Matthew McConaughey is pushing a book to communicate with himself in the past, and they use a fourth dimensional analog to kind of explain how this is working in a temporal sense. But that's not how the fourth dimension really works, nor the fifth dimension, but how would they work if we apply them to a real world system, like, for instance, the hydrogen atom? So today's goal is to find the lowest bound energy of our 5D hydrogenic system using the variational method, which you outlined before in class, and it's not super hard to go through conceptually. The good news about this system, even though it is in 5 dimensions, is that we don't have to worry about 4 of those due to spherical symmetry. And even then, that constant that's going to come out of the integration is just going to be canceled out because we're dividing 2 different integrals that have that same constant. So the hypervolume is going to be 8 pi squared over 15. We don't need that, so we can just go ahead and do an integration with respect to one variable. So we start here. This integral is equal to the following. We're integrating from 0 to infinity out in this hydrogen shell. We have our wave function, applies to Hamiltonian, which we know is up here. And in this case, I'm just going to go ahead and throw in our v, or dimensionality, which is 5 in this case. So we're going to end up getting 1 over r to the 4th times the derivative of, in this case, it's going to be r to the 4th times the derivative of our wave function. So that's going to be negative b a e to negative br. And then we have this potential term minus k a e to negative br over r cubed. And the only thing we can worry about in terms of the Jacobian is this r to the 4th factor right here. That's left over from the integration of integrating over something in 5 dimensions. And that's with respect to r. So we mentioned it before, but that solution for that trial wave function is important because that's the exact solution in our 3-dimensional case, which we've already established before. So it makes sense to use the exact same wave function in a 5-dimensional case, see what happens. So we go through, and then just for clarity, we're going to end up getting an integral r equals 0 to infinity of, again, this backdrop in front, times h bar squared over 2m, times, and then we're going to carry this through after doing the derivative. You're going to end up getting negative 4 over r times b a e to negative br plus d squared a e to negative br, and then you still have this potential term over here, a e to negative br over r cubed, r to the 4th dr. And once you evaluate this integral, using everyone's favorite theory, Wolfram's theory, you end up getting the following. You're going to get negative a squared 2b kn minus 3h bar squared all over 8 times b cubed times n. So that's just the first part of our method. We have to do the second integral, which is just the side states together. So this one's a little more straightforward to go through. Same math integration, same Jacobian, just in this case it's a squared e to the negative 2br times r to the 4th dr. And that evaluates to 3a squared over 4b to the 5th. And so before we start varying our parameter b, and for the second part of the variational method, we have to do that division up here. So we end up getting that this relationship over here, this whole crux of the problem, is equal to h bar squared b squared over 2m minus b cubed k over 3. So that's gonna be more in depth in the write-up, but that's what we're looking for, is something like that we can throw in to figure out what the values of E over D allow for this. And then throw it back into our solution to see what the lowest excited energy is. Not lowest excited energy, the ground state. So we can go ahead and figure out what this is. So take the derivative with respect to B of, in this case, that whole term over there, h squared, b squared over 2m minus e cubed k over 3, and we're going to set it equal to 0. So what that is carried over here. So over here, we can have a better view of this. It's going to be h bar squared times 2b over 2m minus k over 3 times b squared, or times 3b squared. And then that's all equal to 0. Keep carrying it over. We're going to end up getting here in the handwriting, h bar squared b over m minus kb squared. So if we solve for b, we're going to get b is equal to h bar squared over km, or 0, which is going to be important in a minute. So we plug this back into our solution for the expectation value. Over here, we're going to get the following. After plugging this back in, we get h bar squared over m cubed, k squared, sorry, that's a k, times 1/2 minus third, and that is equal to h bar to the 6th over 6m squared times k, or k squared. So that's an answer, and you might be thinking that's okay to go with, but that is a positive answer, meaning that this is a positive energy, and that can't be a bound state. So we can ignore that solution and go with the 0 case, which means that our lowest expected energy should be 0, meaning that there is no lowest bound state of a 5D system. That implies that any amount of energy could kick this into an excited state. So the lowest energy is 0, but that's not a bound state. So that's a little problematic. Maybe this is all resolved in a 4D universe. So we can go through the exact same math, and we get an even more concise answer, which makes this a little more problematic. So we already established what that set looks like, so we can go ahead. H. The only difference in this whole integral is that every time there's a d, it's just going to be 4. So all of those terms are reduced by 1. So we're going to end up getting our integral looks like r equals 0 to infinity of a e to negative br, same Hamiltonian 2m 1 over r cubed, not r to the 4th, d by dr of r cubed negative ba e to negative br inside the parentheses minus our potential term, which now has an r squared in the denominator. K e to negative br all over r squared. And then this time the hypervolume, again, we're not going to worry about the other constant on the outside, but that Jacobian is going to be an r cubed this time, dr. And that is equal to negative a squared times 4km minus 3h bar squared over 16b squared m per Wolfram's theory. Now, we can figure out this product again, except the only difference is that we're doing it with an r cubed instead of an r4, or an r to the 4th term. So this whole integral evaluates out to be 3h squared over 8 times b to the 4th. And then that means that we can go ahead and compute here. This fraction, which gives us h bar squared b squared over 2m minus 2k b squared over 3. And then once again, we're going to vary b. So we're going to be doing this process down here. And then if we vary that, we're going to find that we're going to end up getting h bar squared b over m minus 4kb over 3 equals 0. You notice the only possible solution for this system is if, oh, that's really awful indeed. B must be equal to 0. So if we plug that up into our original problem, we're going to get again the lowest excited or lowest ground state, not the lowest ground state. The ground state should be 0, which is not a ground state because anything can excite that. So we see that in either 5 dimensions or 4 dimensions, the hydrogen atom doesn't have a lowest ground state, which makes it very promising that we live in a dimension where there is ground states to hydrogen that aren't, 0.
When we investigate the patterns of any effective potential for any, d-dimensional system, we find some really obvious and really interesting things. So, right, this is the dimensionality of our system right over here. D equals 3. The K is irrelevant, it's just the strength of our charge. M, again, is irrelevant, it's just the constants. Now we get this equation right here. So that's our potential in any dimensions. That's that 1 over, x to the, dimensionality minus 2. So, r minus 2 in our equations, r to the d minus 2. And then we have this part right here. That's where the effective potential comes in. And I found this using physics stack exchange, and where J is equal to the orbital angular momentum number. And then it's added to this constant right here, this dimensionality, minus 3 over 2. And so we're in dimension 3. And what we notice is that in dimension 3, there is that lowest bound state of an effective potential. If we raise this value up a little bit, right, we see that classic effective potential where we have these bound states that would be in this well and then a maximum at some point over here. If we kick this up to 4, we see there is no clear bound state, right? It asymptotes down to infinity down here. We can scroll it down a little bit right here. That's just kind of asymptotes, right? So that's why we see there's no bound state for the system. If we go up to 5, we see that we have this little spike right here. And that corresponds to that solution we found earlier where there is a solution, but it's not a stable potential. It's not the lowest energy because any kick in any direction is going to excite this, right? So we see that if we keep bumping it up, right? 6 to 7 to 8, we keep seeing this pattern where there's this spike almost, and then those represent the solutions of B when they're not equal to 0, but there's no ground state that we'd speak of. So that was kind of interesting to go through and see. But that's why we don't see those ground states. So as always, thanks for watching.